This lesson's on friction, and here are your objectives. So first, friction acts between two solid surfaces to oppose their motion relative to each other. You can imagine it as a consequence of irregularities in the surfaces of the two objects that interact as you try and slide one in one direction. So we're trying to bring this one this way, or this one in the opposite direction, and these bumps are interacting and trying to oppose their motion. And friction has some interesting properties. Let's take a look at a quick simulation. This simulation is from PhET, and it's called Forces and Motion Basics. I want you to notice that what happens as this person pushes on this box with increasing force. I'm going to increase the force being applied, and watch how right now, let me turn on the values for you, the applied force is always being matched exactly by the frictional force. Those two numbers are the same. As I increase it, they remain the same. So the frictional force is increasing directly with the applied force and matching it. Until I get to a certain point, here I've gotten to 94 newtons, I get above 94, and still being matched, but at a certain point, watch what happens to the frictional force. We see it's dropped off now, down to 94 newtons. It got above 94 newtons, but once I got the object moving, it dropped. So this is a peculiar property of friction that we need to take into consideration. It increases linearly until the object starts moving, and then it drops off. And now, in fact, if I keep increasing the applied force, notice that the frictional force is not getting above 94. It's staying there. And so the net force is increasing, and the object is accelerating. So now let's take that into consideration and graph the force of friction against the applied force. When the object wasn't moving, we saw that as we increased the applied force, the force of friction increased with it. So there's a direct proportionality between those two. However, we got to a certain point where the object started moving, say it starts moving right there, and then the force of friction dropped off. In the example, it dropped off to 94 newtons. So let's say this y value here is 94 newtons, and then it maintained the same value throughout. So here we have the object stationary, and here we have the object moving. So this is the object moving, and over here we have the object stationary. The force of friction when the object is moving is called dynamic friction. And the force of friction when the object is stationary is called static friction. Now notice that dynamic friction remains constant and is lower than the maximum possible value of static friction. Static friction increases with the applied force to a maximum value. In equation form, if this is the force of static friction, and I sometimes write this as the force of static friction, or you could use a lowercase f like that, but you'll see this in your IB formula booklet, it's less than or equal to a maximum value, and that maximum value we can call Fs max, and it's equal to, this is the coefficient of static friction multiplied by the normal force. R for reaction is another way of stating the normal force. So the normal force is determined by the situation, by the mass and the orientation of the object, and the coefficient of friction is determined by the two surfaces that are in contact. So this value here is Fs max, and the value, the y value is Fs max, and the force of friction can take any value up to that. The force of static friction can take any value up into that. That's why we have a less than or equal to sign. To calculate that value, we would need to be given this coefficient of static friction, and we would have to work out the normal force from the problem. Now here, the force of dynamic friction, I sometimes write this as F sub d, or you could use lowercase f sub d, is equal to, similarly, the coefficient of dynamic friction multiplied by the normal force. And you can see here that the coefficient of dynamic friction is generally lower than the coefficient of static friction. This value for static friction is higher than the constant value for dynamic friction. Let's take a look at a problem. We've got a 10 kilogram box resting on a horizontal floor. There's our horizontal floor, and there's our 10 kilogram box. The coefficient of static friction is given here, and the coefficient of dynamic friction is given there. Find the force of friction acting on the box if an external horizontal force is exerted on the box with these changing magnitudes. So I'm going to be increasing this force that I am pulling with, and the question is, what's happening over here? So let's first work out what is Fs max, because that will tell us how much force we can apply before the object starts moving. So Fs max is going to be, just use the equality from the formula above. I'm going to write normal force instead of reaction force, but it's the same thing. That's going to be equal to 0.40, that's what we're given right here, multiplied by the normal force. And in this case, the object is on a level, and we've got the weight operating downwards, mg, and the normal force must be equal and opposite to the weight because the object is not accelerating in the vertical dimension. Therefore, the magnitude is the same as the weight, which is going to be 10 kilograms, the mass multiplied by 9.81 meters per second squared. You do have to be a little bit careful that if this were on an angle, if this were on an angle like that, the normal force is not going to be equal and opposite to the weight. So that can get a little bit tricky, but that's not the situation that we have here. Carrying on, if we calculate that out, we get 39.24 newtons, or to two significant figures, 39 newtons. That means that as I increase this force, the static frictional force can increase to a maximum of 39 newtons. That's going to be where this peak is right here at 39 newtons. And then after that, the box is going to start moving, and I would expect the frictional force to drop off. So if I apply a 0 Newton force, the object's not moving. The frictional force, again, is static friction, and remember that it's going to be exactly equal to the applied force until I get to Fs max. So this is below Fs max, so if I apply a 0 Newton force, I get a 0 Newton frictional force. If I apply a 10 Newton force, I get a 10 Newton frictional force. 20 newtons, same thing. I'm just moving up the diagonal part of the graph. 38 newtons is actually still below this, so I get a 38 Newton static frictional force. All of these cases are force of friction is static friction. The object is not moving yet. However, once I cross 39 newtons, the object is going to start moving, and now I'm into the dynamic friction situation. So here, 40 greater than 39, I'm going to be moving, and I need to do a new calculation. I need to figure out what the force of dynamic friction is. And the force of dynamic friction, we just followed the same procedure above, is going to be equal to the coefficient of dynamic friction now, multiplied by the normal force, and that's going to be equal to 0.30, and by the same reasoning as above, times 10 kilograms times 9.81 meters per second squared. And when I work that out, I get to two significant figures. I get 29 newtons. So when I apply a 40 Newton force and the object starts moving, instead of getting the maximum static friction, because it's moving, it's dropped down to 29 newtons. So I get a 29 Newton dynamic friction force. So there's an example where we needed to think through exactly what's happening in terms of the object's movement. Let's look at another example. This is a Newton's second law type problem that incorporates friction. We've got a skier skiing down a slope with a 30-degree elevation. We're given the coefficient of kinetic friction, and we're asked to find the acceleration. Notice that we're not given the mass, which implies that we are not going to need it. So let's draw our situation. There's our ski slope. We've got a 30-degree incline. And remember that we always want to orient our coordinate system so that acceleration goes along one of the axes. So we're going to orient it like this. And the forces acting on the skier are going to be her weight in the vertical direction, pointing downwards, and normal force. Notice that those two are not going to be equal in magnitude. And we've got a force of friction that is going to be operating up the slope. Now, remember that if this is 30 degrees, this is also going to be 30 degrees in here, like we've seen with these inclined plane problems before. Let's think about the vertical dimension for a moment. I'm going to write f net y like this for a change. This is the same as f net y. And we know that she's not accelerating in this direction. Now she is coming down the slope, but we've angled our axes so that that is only in the x dimension. So the sum of the forces in the y direction must be equal to 0. It's not levitating off or being pulled into the slope. And the forces acting in that direction are the normal force acting upwards and the component of the weight along this line. And therefore those two must be equal and opposite to each other. The normal force must be equal to mg cos 30 degrees. And that's all we can do right now with that, but we're going to use that in a moment. If we look at the F net in the x direction, we're going to use this direction as the positive direction because that's the way that she's going to be moving. So we need now the other component of the weight. So her weight sine 30 degrees minus the force of friction that's pointing up the hill and opposing that motion. That's the net force. And by Newton's second law, that must all be equal to her mass times her acceleration. Now, the frictional force is equal to the coefficient of dynamic friction, because she's moving, multiplied by the normal force. And the normal force we worked out up here. So we're going to sub that in. MA is equal to mg sine 30 degrees minus 0.1 is the value that we're given in the question, and the normal force is equal to mg cos 30 degrees. There's our equation. Now, notice that at this point, mass cancels out, so we didn't need to know her mass. And the acceleration is equal to g sine 30 degrees minus 0.10 g cos 30 degrees. And plugging in 9.81 for g and solving, we get that her acceleration is equal to 4.055 with some more stuff, rounded to two significant figures, is 4.1 meters per second squared, and that's got a direction of down the slope. So you can see how we can use friction and Newton's second law along with free body diagrams to solve some problems.